Up to this point, the nuclear processes that we've been looking at have been taking atoms and breaking them into smaller pieces or converting them into something else that has the same size. So beta emission, positron emission, we don't really break the thing into smaller pieces. They are technically losing a particle, but the mass stays the same. Alpha decay, you do lose a little bit. You lose a little chunk of matter with that type of radioactive decay. But you can actually do the reverse process. If you have a whole lot of money and you feel the hankering to make yourself some new atoms, you can build yourself one of these things, a particle accelerator. And you can use those to fuse nuclei together. This is what we call nuclear transmutations. Um, you put these particles into an accelerator, and you get them whipping around that accelerator at practically the same speed as light. It's not technically at light speed, but it gets really close to the speed of light. And then you just smack those things into each other, and they collide with such force that the nuclei will sometimes fuse together. And when this happens, not only do you get things fused together, but then they lose some other stuff as well. And so there's a little bit of a notation here for like the thing that you're shooting the particles at, the thing that you're shooting it with, which is alpha particles in this case, and then the thing that gets shot out of the resulting product that you make. And so in the end, here in this particular process, you would be making oxygen-17 by shooting an alpha particle at some plain old nitrogen. So this was actually done first by Rutherford back in 1919, getting particles to collide together at high velocities to form new stuff. We do it much more efficiently than they did back then, but it's a very intensive process. It takes a lot of time, a lot of money, but it gives you some really cool results, and not just in terms of making new stuff. You can get a lot of very intricate physics data from this as well, understanding how subatomic particles work, not just making new atoms, but understanding the building blocks of atoms as well. And so these things are just absolutely ginormous constructions. They can have radii that are miles long. So you can see there's a forest in the middle of this accelerator. And not just is it amazing because of its size, it's amazing because of the absolute precision that has to be used in building these things. Like, you have this construction that is miles in size in terms of its dimensions, and you can't be off by millimeters in the construction of it. These things have to be so precisely built that they literally take the curvature of the Earth into account when building these rings. They have to be that precise. It is really amazing. But this is how you would make big atoms, as well as, like I said, other stuff. Everything that is bigger than uranium that exists, as far as we are aware anyway, in the universe, everything that is bigger than uranium was created here on this Earth. So unless there's some aliens out there that are doing the same thing as us, the biggest atoms in the universe actually exist here on Earth. Again, as far as we are aware. So everything bigger than uranium was produced in a lab somewhere. This data here is a little bit old because this says that the largest proven element was copernicium, I think is how that's pronounced. But that is not true anymore. I believe the biggest one is now nihonium, or maybe it's oganesson. I forget. There's some new elements that were just accepted within the last couple years. I haven't updated this slide, obviously. Actually, I did update it once, but then I lost that file where I had it updated, so now it's back to the older version. But regardless, copernicium, the one that was the largest for a while, it was produced by continuously bombarding a piece of lead with zinc atoms for 3 weeks, and they made a single atom that was detected for 100 microseconds. That's 1,000th of a second. So they bombarded lead with zinc for 3 weeks, made a thing that lasted for like literally less time than it takes you to blink, and it's on the periodic table now, which is kind of crazy to think about. Now, that being said, it was reproduced. For something to get on the periodic table, it does have to be made by more than one lab. I forget if it has to be 3 or 4, but I believe it is more than 2 different labs have to create the thing, have to verify the process for making that element before it gets on the periodic table. But even in those situations, like, it didn't last for hours or anything. It was, again, just it's there and then it's gone. But it did exist. It existed for that 100 microseconds, which at the atomic scale is actually not as short of a time as it seems for our time scales. Atoms do a lot of stuff in 100 microseconds. Right. So let's talk about some applications of nuclear chemistry. So one thing that is very useful about radioisotopes is that they can be really easy to track. Because they're so energetic, because you can detect them decaying, it can be very useful for tracking things if you're able to put what we call a radio tracer into the molecule. And I'm not talking about like secret agent stuff, putting a radioactive tracer on a briefcase so you can follow the bad guys or whatever. No, I'm talking like I want to figure out which carbon is reacting in this particular reaction that I'm looking at. And so I'm going to make, of the 7 carbons in the molecule, I'm going to make 6 of them plain old carbon, and then I'm going to make this carbon carbon-14. And I'll be able to track where that carbon-14 goes, because it will behave slightly differently than all the other carbons, because it is radioactive. And so those are the types of radio tracers that I'm thinking about, which is what it's discussing here. So if you have a radioisotope placed on a molecule that takes part in a series of reactions, a scientist can trace exactly where that molecule goes when it might not be possible otherwise. And so organic chemists, like I said, if they're trying to track which carbon is participating here, or if it's even a larger thing, like maybe there's a chlorine, if there's multiple chlorines and you're considering, which chlorine is it, you could put a radioactive chlorine into the mix. It doesn't have to be a lot where it's dangerous, just a very small amount. And you can track where that goes if you know where it started in the first place. Another useful thing for radioactive materials is in certain medical applications. I know I briefly mentioned PET scans at the beginning of this chapter, but the reason that we use PET scans, or I guess I shouldn't say the reason, but the process through which we use PET scans is we have some kind of molecule, and I believe, and I could be wrong about this, so double check me on this, but I believe usually what's done is you attach a radioactive isotope that is going to undergo positron decay, and you attach it to sugar, I believe. Because cancer cells use a lot more energy, those sugar molecules will I guess you could say preferentially go to that area, that more of them will go to those areas than they would do the rest of the body. And again, you can double check me on that, but I believe it's as simple as that. I think that at least in some situations, they can just attach them to sugar molecules and then watch where those sugar molecules go to get consumed. And they can image where cancer cells are, because when that radioactive isotope decays and produces a positron, there's a whole bunch of electrons all around. And as soon as that positron impacts an electron, they're going to annihilate each other. And it's going to give you a burst of two gamma rays shooting out in opposite directions, and that gamma ray burst going off in opposite directions can be detected, and based on which detector sees it and the time differential from one side to the other, they can actually image both like all the dimensions of where those gamma rays were produced in the first place. So they can map out where those radioactive isotopes were taken in the body, which is really cool and also kind of really scary. Which is not to, if at some point your doctor tells you you need a PET scan, get a PET scan. He wouldn't be telling, or she wouldn't be telling you that unless you really needed a PET scan. But it is kind of scary, but also cool to think about how you're taking this PET scan and you literally have gamma rays shooting out of your body. It's kind of spooky and cool at the same time. Alright, I think we'll call it there for this video. In the next one, we're going to get into nuclear binding energies, which is also kind of spooky, but in a different way. So I'll see you in the next video.